In the summer of 1944, a massive, unrecognizable silver bomber plummeted into the remote fields of mainland China. When Japanese intelligence officers and aeronautical engineers scrambled to the wreckage, they expected to analyze a conventional enemy warplane. Instead, as they pulled twisted, pressurized aluminum from the dirt, they encountered a level of technological integration that defied their entire understanding of wartime logistics. They were not merely looking at an airplane, they were staring at an industrial anomaly, a machine built with a complexity that, according to Japan's own resource projections, should have been physically impossible to mass produce. What the Japanese recovery teams hauled out of the Chinese dirt and transported back to their aviation laboratories was not merely a captured weapon, it was a forensic blueprint of their own defeat. To understand how completely the balance of power had shifted in the Pacific, we must look at exactly what these engineers discovered as they systematically dismantled the Boeing B-29 Superfortress. Piece by piece, they stripped away the scorched aluminum to reveal a terrifying reality. They found pressurized bulkheads that allowed American crews to fly and fight in the freezing stratosphere, miles above effective interceptor altitudes. They uncovered a network of remote-controlled defense turrets driven by advanced analog fire control computers, a complex nervous system of wiring and servos that calculated wind speed, gravity, and target lead in a fraction of a second. These were not handcrafted experimental prototypes. They were highly sophisticated components engineered specifically for relentless, standardized mass production. How did the careful dissection of this single, battered airframe force Japan's elite aeronautical minds to confront their situation? And why did the microscopic tolerances hidden inside this wreckage prove that the collapse of the Japanese Empire was no longer a military possibility, but an unavoidable industrial certainty? To comprehend the shock that rippled through the Japanese engineering teams analyzing the wreckage, one must first look at the deteriorating reality on their own factory floors by the summer of 1944. The Imperial Japanese aviation industry was slowly and systematically suffocating. The agile, lethal fighter planes that had dominated the Pacific skies during the early years of the war, like the Mitsubishi A6M0, were designed for an entirely different kind of conflict. They were brilliant machines of aerodynamic grace, optimized for low and medium altitude dogfights, built by a pre-war generation of master craftsmen. But the air war of 1944 was no longer a contest of individual pilot skill. It had become a ruthless battle of mass production, raw materials, and thermodynamic engineering. And in this arena, Japan was bleeding out. An ever-tightening American submarine blockade was effectively choking off the supply of critical imported resources. Aviation fuel was no longer the high-grade, high-octane lifeblood required for advanced, high-performance engines. Japanese refineries were struggling to produce even 87 or 91 octane gasoline, while the Americans were consistently burning premium 100-octane fuel in abundance. Duralumin and other critical light alloys were heavily rationed, forcing designers to compromise structural integrity. Even worse was the catastrophic drain on human capital. The experienced machinists, master riveters, and seasoned factory foremen who had built Japan's early air fleets had been drafted and sent to die in the jungles of New Guinea or the Solomon Islands. In their place stood conscripted high school students and unskilled laborers trying to operate aging machinery that was rapidly wearing out and losing calibration. Under these crushing domestic conditions, the Japanese military had issued a desperate mandate: develop high-altitude interceptors. Intelligence reports had been warning of a new, massive American bomber for over a year. The Japanese High Command knew this impending threat would not fly low over the home islands. It would come from the stratosphere. But reaching 30,000 feet and actually maintaining combat performance there are two completely different aerodynamic problems. At 30,000 feet, the air is freezing, thin, and starved of oxygen. To make a piston engine function in that brutal environment, an aircraft requires a turbo supercharger, a mechanical lung that uses exhaust gases to spin a turbine at more than 20,000 revolutions per minute, forcing compressed, oxygen-rich air back into the engine block. Building a reliable turbosupercharger is not a matter of engineering theory or pilot courage. It is a strict, unforgiving test of advanced metallurgy and precision tooling. The turbine blades are subjected to searing exhaust heat on one side and sub-zero atmospheric temperatures on the other. Japanese metallurgists simply did not have the heat-resistant alloys, the tungsten, the cobalt, the nickel, needed to cast these blades so they wouldn't warp, melt, or shatter under extreme thermal stress. And even when they attempted to substitute materials, their machine shops lacked the microscopic precision tooling necessary to mass-produce the components at scale. As a result, Japanese high-altitude interceptor programs were plagued by endless delays, failing prototypes, and engines that literally choked to death in the thin air. Japanese test pilots found that pushing their aircraft above 25,000 feet felt like flying through molasses. The planes lost speed, the flight controls grew dangerously sluggish, and the engines sputtered, starved of the very atmosphere they needed to burn their inferior, low-octane fuel. While Japan's aeronautical sector was fracturing under these physical constraints, the United States was executing a totally different industrial doctrine across the Pacific. The U.S. War Department, driven by the relentless vision of Army Air Forces General Henry Hap Arnold, had initiated the Very Long-Range Bomber Program. They had committed an unprecedented $3 billion to the Boeing B-29 Superfortress project. To put that staggering figure into perspective, it was $1 billion more expensive than the top-secret Manhattan Project that developed the atomic bomb. The Americans were not merely designing an airplane. They were creating a pressurized, heavily armed battleship, engineered to operate exclusively in a sanctuary where the enemy could not survive. The American engineering philosophy was brutal in its simplicity. Why fight the agile Japanese interceptors if you could build a machine capable of simply flying over them? The Japanese defense network was fundamentally unequipped to handle this reality. Their early warning radar systems were rudimentary, lacking the range and resolution to track high-speed, high-altitude armadas. The standard Japanese anti-aircraft weapon, the Type 99 88mm flak gun, was painfully inadequate for the task. Its shells struggled to reach an effective bursting altitude of 25,000 feet, and the mechanical fire directors were far too slow to accurately track a bomber moving at nearly 350 miles per hour in the stratosphere. To the military planners in Tokyo, the arithmetic of the sky was turning deeply against them. The Americans were weaponizing the very atmosphere, preparing to deploy a fleet that would operate entirely above the physical reach of the Japanese Empire. This was the grim context weighing on the minds of the Japanese engineering teams as they transported the tangled, pressurized wreckage of the fallen B-29 from the Chinese dirt to their laboratories. They were finally holding this $3 billion phantom in their hands, desperately searching for a mechanical weakness they could exploit before the home islands were turned to ash. The search for a fatal flaw began in earnest at the Tachikawa Army Air Arsenal in the western suburbs of Tokyo, where the mangled components hauled out of China were carefully laid out for inspection. The aeronautical engineers first directed their attention to the intact sections of the pressurized crew compartments. They expected to find rudimentary sealing methods. Instead, they discovered a heavily reinforced, self-sustaining environment built with microscopic manufacturing tolerances. The Americans had effectively constructed a lightweight pressure vessel capable of flying through the stratosphere, utilizing advanced rubber gaskets, synthetic sealants, and meticulous flush riveting techniques that maintained internal cabin pressure despite the severe structural flexing of combat maneuvers. But the true revelation, the discovery that fundamentally shattered the morale of the investigating teams, came when they dismantled the bomber's defensive armament. The Superfortress was not defended by gunners standing behind open windows in freezing winds. It was protected by a synchronized network of remote-controlled turrets, all tethered to a centralized electronic nervous system. When Japanese technicians opened the sealed units controlling these turrets, they found General Electric analog computers. Inside was an intricate maze of servos, gyroscopes, and electrical relays designed to automatically calculate airspeed, gravity drop, target lead, and parallax, instantly aiming the machine guns with mathematical precision. The fundamental science behind this machinery was not an alien concept to Japan's intellectual elite. When the salvaged components were brought to the leading physicists and electrical engineers at Tokyo Imperial University, the researchers quickly grasped the underlying principles. They fully understood the complex mathematics and physics governing the analog fire control circuits. They knew exactly how the machine worked. And that was precisely why the discovery was so devastating. The psychological blow did not come from an inability to comprehend the technology. It came from the crushing realization of how that technology was being manufactured. To the professors at Tokyo Imperial University, an analog computer of this staggering complexity was a delicate, laboratory-grade instrument. In Japan, building even a single functioning unit would require the nation's top scientists working for months, handcrafting and calibrating each individual component in a controlled environment. The wreckage laid out on the floors of Tachikawa proved that the United States had somehow figured out how to take these fragile, hyper-complex scientific instruments and mass-produce them on standardized assembly lines. The Americans were manufacturing laboratory-grade electronics by the tens of thousands, bolting them into combat aircraft and treating them as standard, disposable inventory. They were sending these technological marvels into hostile skies, knowing they might be blown to pieces the very next day, and knowing their factories would simply roll out replacements. For the Japanese engineers staring at the dismantled circuitry, treating highly sophisticated electronics as expendable combat components was incomprehensible. It signaled a scale of industrial dominance that no amount of tactical brilliance could ever overcome. As the forensic dissection at the Tachikawa Army Air Arsenal moved from the highly classified electronic nervous system to the physical anatomy of the airframe itself, the Japanese aeronautical engineers encountered a masterclass in aerodynamic efficiency that further separated American manufacturing from their own desperate reality. They ran their hands over the massive exterior skin of the bomber's fuselage and wings, noting a structural feature that was exceptionally difficult to achieve on such a staggering industrial scale: universal flush riveting. Every single B-29 Superfortress required well over 1 million individual rivets to securely hold its stress skin aluminum panels together under the immense aerodynamic loads of high-altitude flight. In standard aviation manufacturing across the globe, including the vast majority of Japanese bomber and fighter production, most rivets were simply driven in and left with rounded, dome-like heads protruding slightly from the metal surface. It was a faster, cheaper, and structurally sound method of building an airplane. But at cruising speeds approaching 350 miles per hour, those millions of tiny metallic domes created an immense amount of parasitic drag, catching the wind, slowing the aircraft down, and burning precious, irreplaceable aviation fuel. To eliminate this microscopic but cumulative drag, American factories had employed countersunk flush riveting across the vast, shining surfaces of the bomber. This required precision machine tools to perfectly dimple the aluminum skin at every single rivet hole, so that when the fastener was driven in, its head sat perfectly flush with the aerodynamic profile of the wing. Executing this on a small, handcrafted racing plane or a single experimental prototype was one thing. Executing it flawlessly across a 100-foot pressurized fuselage on a moving assembly line churning out hundreds of aircraft a month was an entirely different industrial reality. The Japanese investigators meticulously measured the seams, the joints, and the rivet lines. The microscopic, unvarying tolerances proved beyond a shadow of a doubt that American sheet metal presses and automated pneumatic riveting machines were operating with a level of mechanical consistency the Japanese factory managers, currently relying on drafted high school students, could only dream of achieving. Beneath that perfectly smooth aluminum skin, the skeletal structure of the massive bomber revealed another critical, disheartening disparity: the aggressive and extensive use of advanced magnesium alloys. Magnesium is roughly 1/3 lighter than standard aviation aluminum, but extracting, smelting, and casting it into usable, stress-bearing components requires an enormous, stable supply of electrical power and highly specialized modern metallurgical foundries. The American engineers at Boeing had relentlessly integrated complex magnesium castings throughout the B-29's design, utilizing the lightweight metal in the heavy engine nacelles, the supercharger housings, the enormous wheel assemblies, and various structural bulkheads. By systematically stripping thousands of pounds of dead weight from the heavy airframe through advanced metallurgy, the designers allowed the bomber to carry significantly heavier fuel loads and much larger, more destructive bomb bays. Japanese metallurgists, carefully examining these recovered castings, understood the underlying chemistry and physics perfectly. Japan possessed its own domestic magnesium reserves, but the national power grid, which was heavily reliant on highly vulnerable coastal coal shipments and aging, overtaxed hydroelectric plants, simply could not support the massive, energy-intensive smelting processes required to produce these lightweight alloys in meaningful, standardized wartime quantities. They knew how the metal worked, but they lacked the raw industrial calories to forge it. The internal logistics of the airframe exposed an even deeper, more profound philosophical divide in how the two warring nations fundamentally built their machines. When the Japanese investigators tore into the pressurized bulkheads to examine the intricate electrical and hydraulic systems, they did not find the familiar chaotic tangle of point-to-point wiring that characterized almost all combat aircraft of the era. Instead, they discovered a highly organized, modular system of prefabricated wiring looms. The American engineers had bundled literally miles of complex electrical cables into thick, neatly bound harnesses, wrapped them tightly in protective, rubberized conduits, and fitted the ends with standardized, quick disconnect multi-pin plugs. This was not merely an aesthetic design choice to keep the interior looking clean. It was an absolute revolution in mass production and frontline combat maintenance. In a typical Japanese aviation plant, a highly skilled electrician had to manually route, solder, cut, and test individual lengths of wire inside the cramped, dark fuselage of a bomber, a notoriously slow, frustrating, and labor-intensive craft that created immense production bottlenecks. The American modular method allowed a completely unskilled factory worker in a Kansas or Nebraska assembly plant, perhaps a civilian who had never even seen an airplane up close 2 years prior, to simply grab a pre-assembled, factory-tested wiring harness off a rack, lay it into the fuselage channels, and snap the color-coded Amphenol connectors together in a matter of minutes. The battlefield implications of this design were equally terrifying to the Japanese analysts. If a B-29 sustained heavy anti-aircraft flak damage to its electrical system during a bombing run over the Pacific, a mechanic stationed on a forward base in the Marianas did not need to painstakingly trace and splice a dozen severed, burnt wires in the dark with a soldering iron. He simply unplugged the shredded, ruined wiring loom, tossed it in a scrap pile, and snapped a pristine, factory-fresh replacement harness into the sockets. This plug-and-play architectural philosophy meant that the Superfortress was engineered not just to fly high and drop bombs, but to be built rapidly by untrained amateurs and repaired almost instantly in the unforgiving conditions of a forward combat zone. Yet, for all this intimidating, unprecedented industrial sophistication, the rigorous forensic analysis at Tachikawa also revealed that the B-29 was far from a flawless, invincible machine. As the heavy engineering teams hoisted the massive, scorched remnants of the bomber's 4 power plants out of the tangled wreckage, they uncovered a brutal, highly lethal reality about the American war effort. The engines powering the bomber were Wright R-3350 duplex cyclones, colossal, highly complex, 18-cylinder radial monsters, capable of generating over 2,200 horsepower each. But the physical evidence pulled from the Chinese dirt proved they were also profoundly, dangerously defective. By minutely examining the burnt exhaust valves, the warped cylinder heads, and the heat-scarred metallic cowlings, Japanese propulsion experts quickly identified a severe, fundamental thermodynamic flaw in the Wright engine's internal design. The rear row of 9 cylinders was packed far too tightly behind the front row, heavily obstructing the critical flow of cooling air over the cooling fins. In the thin, freezing, oxygen-starved atmosphere of the stratosphere, where the bombers were designed to operate, this lack of airflow caused the rear cylinders to chronically, violently overheat. Furthermore, the Americans had utilized that highly flammable magnesium to forge the engine crankcases in order to save overall weight. The Japanese engineers recognized this immediately as a terrifying, potentially suicidal combination. Magnesium is notoriously difficult to ignite under normal circumstances, but once it reaches its extreme ignition temperature, often triggered by a routine, localized engine fire stemming from those overheating rear exhaust valves, it burns with the blinding, unstoppable, self-sustaining ferocity of a thermite flare. A magnesium crankcase fire could easily reach temperatures exceeding 3,000 degrees Fahrenheit in a matter of seconds, acting like a giant blowtorch that could effortlessly melt right through the bomber's main aluminum wing spar, causing the aircraft to literally tear itself apart and disintegrate in midair. The wreckage recovered from the mainland bore the unmistakable, catastrophic burn patterns of exactly this kind of intense magnesium fire. The Japanese investigators realized that the United States Army Air Forces had not achieved engineering perfection at all. In their desperate, calculated rush to field the very long-range bomber and bring the Japanese home islands within striking distance, the American command had knowingly pushed a highly unstable, notoriously fire-prone engine into mass production and frontline combat. They were willingly sending hundreds of their own highly trained air crews to potentially burn alive in accidental, non-combat engine fires over the vast expanse of the Pacific Ocean, simply because the strategic timeline of the war demanded it. But instead of providing any strategic comfort, this dark realization only deepened the sense of existential despair within the Japanese engineering corps. The American logistics and production chain was so overwhelmingly, unfathomably massive that it could simply absorb the horrific attrition rate and catastrophic failures of the Wright R-3350 engines without slowing down. If a bomber's engine burned out, swallowed a valve, or caught fire after only 20 hours of combat flight, the Americans did not halt the bombing campaign to completely redesign the power plant. They simply manufactured and shipped tens of thousands of spare, complete replacement engines across the Pacific Ocean and bolted them onto the grounded airframes directly on the tarmac. The Americans were treating highly complex, multi-million-dollar aviation assets, engines that Japanese industry could barely comprehend, with the exact same disposable, relentless mindset as standard rifle ammunition. Driven by a mixture of institutional panic and the rapidly mounting pressure of the impending, inevitable bomber offensive, the Imperial Japanese High Command issued a predictable yet utterly desperate military mandate: reverse engineer the captured American technology. Intelligence officers, munitions bureaucrats, and Army generals demanded that the domestic aviation industry immediately absorb the hard lessons of the crashed B-29. They wanted a direct Japanese equivalent built, or at the very least, they ordered the immediate integration of the bomber's advanced targeting computers, exhaust-driven superchargers, and cabin pressurization systems into a brand new fleet of heavy, high-altitude home defense interceptors. The impossible task fell squarely onto the shoulders of the elite aeronautical engineers at the Nakajima Aircraft Company and the various military technical research institutes scattered around Tokyo. Their official response to the high command was a brutal, highly documented, and heavily classified assessment of Japan's fatal industrial limitations. The Japanese engineers explicitly stated that they did not lack the mathematical genius, the basic physics, or the aerodynamic theory to understand the American designs. The schematics were clear. What they lacked was the fundamental physical and economic reality to actually execute them. In secret committee meetings and classified stamped production reports, the lead designers laid out the insurmountable, cascading barriers to duplicating the advanced technology. To successfully cast and replicate the General Electric analog fire control computers, or to forge the high-speed turbine blades for the exhaust-driven turbo superchargers, Japanese metallurgical foundries desperately required specific, high heat-resistant heavy alloys. Those vital alloys required a massive, uninterrupted flow of rare imported metals, specifically tungsten, cobalt, nickel, and molybdenum. But the relentless, highly effective American submarine blockade currently strangling the South China Sea had practically severed the vital logistical arteries connecting the Japanese home islands to the resource-rich, occupied territories of their conquered empire. The bulk cargo ships carrying these critical, irreplaceable ores were currently resting at the bottom of the ocean, torpedoed before they ever reached a Japanese port. Even if, by some miraculous logistical breakthrough, the raw materials could suddenly be sourced and safely delivered to the mainland, the Japanese machine tool industry itself was in a state of terminal, irreversible collapse. The microscopic, exacting manufacturing tolerances observed by the investigators in the B-29's automated defense servos, its pressurized cabin seals, and its complex engine reduction gears could only be accurately cut by utilizing modern automated precision lathes, hydraulic presses, and high-speed milling machines. The United States possessed vast, sprawling factories entirely filled with these modern machines, all perfectly calibrated, heavily lubricated, and running constantly on continuous, completely stable electrical power. Japanese aviation plants, meanwhile, were entirely reliant on aging, obsolete, belt-driven lathes that had been imported from Germany or America long before the war began. These irreplaceable machines were rapidly losing their fine calibration, wearing out under constant use, and breaking down entirely, with absolutely no spare parts or replacement tooling available anywhere in the empire. As the detailed technical report circulated, the Japanese analysts watched their initial, deeply ingrained skepticism regarding the B-29 completely transform into a paralyzing, systemic anxiety as they finally comprehended what each individual bomber truly represented. It was not merely a single, standalone weapon of war. It was the final, unified output of an entirely integrated, untouchable continent. The investigators realized that every single B-29 required the seamless, perfectly timed coordination of massive aluminum smelters in Alcoa, sprawling synthetic rubber plants in Akron, pristine electronics laboratories in New York, and gargantuan final assembly facilities in Kansas and Washington state, all physically linked by a massive, untouched, and highly efficient continent-wide railway network. The Japanese engineers were not simply examining a crashed bomber. They were examining the focused, unified industrial might of the entire North American landmass, condensed and weaponized into a single aerodynamic shell. This stark contrast was agonizingly apparent when the engineers compared the wreckage to the daily realities on their own factory floors in Nagoya and Tokyo. The analysts meticulously documented how American standardized mass production allowed for the continuous, uninterrupted generation of thousands of identical, mathematically perfect aircraft. The concept of absolute, uncompromised component interchangeability was the true bedrock of the American war machine. A heavy aluminum wing flap, manufactured by a subcontractor in Wichita, Kansas, would flawlessly align with the pre-drilled rivet holes of a fuselage section built 1,000 miles away by a completely different workforce in Seattle, Washington. Japanese aviation manufacturing, by stark contrast, remained hopelessly bogged down in an outdated, romanticized culture of bespoke, hand-fitted craftsmanship. While this intense dedication to individual artistry had produced aerodynamically exquisite, highly lethal fighter planes early in the war, it had become a catastrophic liability in a brutal war of absolute industrial attrition. Because Japanese factories critically lacked high-capacity precision stamping presses, sheet metal exterior components varied slightly from batch to batch. When a curved engine cowling or an aluminum wing panel arrived on a Japanese assembly line, it rarely fit perfectly onto the airframe on the first try. It required the presence of an experienced master craftsman wielding a wooden mallet, a metal file, and an assortment of tiny metal shims to painstakingly pound, bend, cut, and coax the metal into its final place. Because of this deeply ingrained manufacturing method, absolutely no two Nakajima Ki-84 fighters or Mitsubishi Zeros rolling off the final assembly line were exactly, perfectly identical. They were individual, highly customized pieces of deadly airborne artwork. This meant that if a Japanese aircraft sustained heavy combat damage to its tail section during a dogfight, a field mechanic could not simply unbolt the ruined section and quickly snap on a standard factory-issued replacement. The replacement part physically would not fit. It had to be carefully custom-fitted, filed, and hand-drilled by a master mechanic on the airfield, a highly trained mechanic who, by the summer of 1944, had most likely already been drafted into the infantry and killed in action on a remote jungle island. As the exhaustive, highly classified forensic reports from the Tachikawa arsenal were finally compiled, bound, and circulated among the absolute highest echelons of the Japanese military research bureaucracy, the final, inescapable truth settled heavily over the nation's defense planners. The entire investigation into the crashed B-29 had originally begun as a desperate search for a mechanical vulnerability, a critical engineering flaw that the home defense interceptor squadrons could easily exploit. Instead, the thorough, unforgiving autopsy of the American bomber had ruthlessly exposed the fatal, unfixable vulnerabilities of the Japanese empire itself. The planners realized with absolute certainty that their own national defense infrastructure was effectively, irrevocably broken. The highly touted high-altitude interceptor programs, designed specifically to act as the impenetrable shield against this terrifying new threat, were completely paralyzed by the exact same material shortages and precision tooling deficits that the B-29 wreckage had just highlighted. Existing Japanese fighter planes, starved of the high-octane aviation fuel required to generate combat power, and critically lacking the reliable turbo superchargers needed to breathe, physically could not achieve the necessary operational ceiling to engage the heavily armed Superfortress on its own terms. Calculating the physical intercept geometry revealed a mathematically impossible suicidal task for the home defense forces. By the time the rudimentary short-range Japanese early warning radar systems actually detected an incoming massive formation of B-29s and a heavy interceptor squadron like the Ki-45 Toryu scrambled from their defensive airfields near Tokyo, the American bombers would already be cruising comfortably at 30,000 feet. The Japanese pilots would have to spend nearly an agonizing hour violently coaxing their heavy, underpowered, and literally choking engines up into the freezing, thin air of the stratosphere. Once they finally managed to drag their aircraft up to that altitude, their sluggish, aerodynamically unresponsive fighters would barely have enough kinetic energy remaining to make a single, fleeting, highly inaccurate firing pass before the sheer physical reality of the thin atmosphere forced them to stall and dive back down into the lower altitudes, leaving the bomber stream entirely untouched. The Japanese aeronautical engineers had looked deep inside the burnt, twisted machinery of the B-29 and seen the inevitable approaching future. The sovereign skies directly above the home islands were about to be forcefully surrendered, not because the Japanese fighter pilots lacked the extreme courage or the willpower to fight, but because the entire Japanese industrial base had been thoroughly out-engineered, vastly outproduced, and hopelessly outpaced by an enemy civilization that had figured out how to physically mass-produce the stratosphere itself. But the true cost of mass-producing the stratosphere was hidden within the bomber's charred paperwork. While the physical teardown of the Wright engines had already exposed their terrifying tendency to ignite, it was the recovery of the aircraft's maintenance records and the flight engineers' hastily written logs that laid bare the sheer desperation behind the American strategy. Translating the smeared operational data, Japanese intelligence officers uncovered a staggering statistical reality. The Boeing design was not just mechanically unstable, it was an active internal war of attrition. The flight data revealed that American bomber commands operating out of forward bases in China were losing nearly as many fully loaded aircraft to their own catastrophic mechanical failures as they were to Imperial anti-aircraft fire. The Superfortress was so immensely heavy that simply getting it off the runway required pushing the engines to their absolute thermal red lines. If a pilot hesitated, or if a single valve stuck during those crucial seconds of a maximum weight takeoff, the resulting magnesium fire would consume the aircraft and its 11-man crew before the landing gear even retracted. This was the hidden, desperate compromise buried inside the $3 billion project. The American High Command knew they had deployed a machine that was fundamentally fighting against itself. To keep the engines from melting during the grueling, multi-hour flights across the Pacific, American ground crews were stripping away armor plating, reducing defensive ammunition, and forcing the engines to run dangerously lean just to manage the soaring temperatures. The seemingly invincible bomber was, in reality, an operational nightmare teetering on the edge of self-destruction every time it took to the air. For the Japanese analysts, this was a profound psychological pivot. They realized the United States had not magically perfected high-altitude flight. They had forcefully battered their way into the stratosphere through brutal risk tolerance. The Americans were deliberately rushing an experimental prototype into frontline combat, fully accepting that their own technology would claim hundreds of their elite aviators. It proved that Washington was operating on a mercilessly accelerated timeline, one that prioritized the rapid, total destruction of the Japanese home islands above the survival of their own flight crews. Armed with this grim intelligence about the bomber's volatile power plants, Japanese aerial defense commanders executed a desperate, ruthless tactical shift. If they could not out-engineer or outproduce the American aviation industry, they would violently exploit its mechanical fragility in the sky. Home defense interceptor squadrons were ordered to abandon standard dogfighting doctrines. Instead, pilots in stripped-down Kawasaki Ki-45s and Nakajima Ki-44s were instructed to launch aggressive head-on firing passes directly at the B-29's vulnerable Wright Cyclone engines. The objective was no longer to shoot the aircraft down through traditional aerodynamic damage, but to force a single, well-placed round into the rear cylinders, instantly triggering a catastrophic magnesium fire. When ammunition missed its mark, or the punishing high-altitude physics prevented a second firing pass, Japanese aviators increasingly resorted to the ultimate sacrifice. Specialized air-to-air ramming units were formed, deliberately flying their heavy fighters straight into the massive bombers, trading one Japanese pilot for an 11-man American crew. These brutal, localized interception tactics, combined with the relentless, self-inflicted engine fires, began exacting a heavy, bloody toll on the Superfortress formations. But the Japanese strategy fundamentally underestimated the sheer, terrifying flexibility of the American war machine. The United States industrial juggernaut simply absorbed the bleeding, shipped thousands of replacement crews across the Pacific, and prepared to pivot. In early 1945, Major General Curtis LeMay took command of the Mariana-based bomber offensive. Surveying the mounting operational losses and the abysmal accuracy of high-altitude precision bombing through the ferocious Pacific jet stream, LeMay made a staggeringly unorthodox decision. He ordered his crews to stop fighting the stratosphere. The B-29 fleet was ordered to strip out its heavy defensive ammunition, load up on M69 incendiary clusters, and fly at night. Most shockingly, LeMay ordered the massive bombers to descend from their 30,000-foot sanctuary down to a mere 5,000 feet. This single radical maneuver instantly paralyzed the Japanese defense network all over again. Operating at 5,000 feet in the dead of night bypassed the high-altitude limitations of Japanese fighters, but the darkness rendered their visual interception tactics completely useless. More profoundly, LeMay's order voluntarily discarded the very technology that had so deeply terrified the Japanese engineers at Tachikawa. The billion-dollar pressurized bulkheads were suddenly entirely irrelevant. The intricate analog fire control computers and the remote-controlled turret networks were suddenly reduced to useless dead weight. The Americans proved they were not winning simply because they had built a mathematically perfect superweapon. They were winning because they possessed a military infrastructure so vastly resilient that they could take the most expensive, highly engineered aircraft in human history, instantly abandon its defining technological features, and ruthlessly reinvent it mid-war to burn the Japanese empire to the ground. While the night skies above the home islands were systematically ignited by these low-flying armadas, the meticulously catalogued remnants of the original Chinese crash remained spread across the quiet research benches at Tachikawa. For the aeronautical engineers who had spent months dissecting those scorched aluminum panels and complex wiring looms, the destruction of their cities was merely the physical execution of a verdict they had already read. That shattered Boeing airframe had served as a grim, undeniable crystal ball, forecasting the outcome of the Pacific War long before the heavy bomber fleets ever reached Tokyo. Its autopsy had forced a proud, artisanal aviation culture to accept a cold new reality. Modern global conflict was no longer a martial art. Ultimate victory could no longer be secured by the supreme courage of an individual fighter pilot, the absolute dedication of a warrior class, or even the isolated brilliance of a solitary design bureau. The rules of attrition had permanently changed. Survival now hinged entirely on a nation's logistical capacity to standardize, mass-produce, and endlessly iterate highly complex systems on a continental scale. The Superfortress was mechanically flawed, heavily compromised, and prone to lethal self-destruction. But the American industrial base was so unfathomably vast that it could afford to manufacture those flaws by the thousands, absorb the horrific operational losses, and instantly rewrite its entire strategic doctrine without ever slowing down the assembly lines. As the engineers walked through their laboratories, surrounded by the dissected pieces of the bomber, they understood that Japan had not been defeated by a perfect machine. They had been buried under the relentless, overwhelming mathematics of a fully mobilized, industrialized world. When those Japanese research teams first sifted through the scorched, twisted ashes of that fallen superfortress in mainland China, they were desperately searching for a vulnerable miracle weapon they could somehow isolate and defeat. Instead, staring down at the perfectly stamped magnesium casings and the endlessly replaceable wiring looms, they uncovered a much darker truth. They did not find a solitary airplane. They found the undeniable footprint of a unified, continental assembly line, a relentless industrial machine that had already won the war long before the first firebomb ever fell on Tokyo.